Hello everybody, this is Mika Seppälä. In this video I will discuss a paradox of Zeno, a Greek philosopher who lived almost 2500 years ago. The point that I want to make is that Zeno's paradox is not really a paradox, but it is rather a very nice way to find a formula for an infinite sum, which is called a geometric series. Zeno, a Greek philosopher, presented almost 2500 years ago the following paradox. In this paradox, a turtle challenges Achilles, a well-known fast runner, to race and claims that if he, the turtle, has a head start, he will win because Achilles can never catch him. How can that be? Zeno explains, if the turtle has a feet head start, Achilles must first run a feet. During that time, the turtle has run about a over 10 feet. Next, Achilles runs a over 10 feet, and the turtle about a over 100 feet, and so on. So Zeno claimed there will always be some distance between Achilles and the turtle. So the question is, can Achilles catch the turtle? Now assume that the speed of Achilles is s feet per second and that of turtle is q times s feet per second, where q is between 0 and 1. Clearly q is closer to 0 than to 1 in the situation of Achilles and the turtle, but more generally q may be any number between 0 and 1. Now if Achilles runs a feet, then turtle runs q times a feet, because the ratio of the speeds of Achilles and the turtle is q. If Achilles then runs q times a feet, turtle will run q squared times a feet, and if Achilles runs q squared times a feet, turtle will run q cubed times a feet. So let us figure out how far Achilles must run to catch the turtle. The distance between Achilles and the turtle at the beginning is a feet. So Achilles first runs a feet, and during that time turtle runs q times a feet, because the ratio of the speeds is q. Next, Achilles runs q times a feet, because the distance at the second round is q times a, and the turtle in that time runs q squared times a feet. Now the distance between Achilles and the turtle is q squared times a. So Achilles must run q squared times a feet, and during that time the turtle runs q cubed times a feet. So one concludes that Achilles needs to run a plus a times q plus a times q squared plus a times q cubed plus and so on feet to catch the turtle. And Zeno argued that this is an infinite sum. Achilles can never run all this distance and hence can never catch the turtle. So how about that? We of course know that Achilles will catch the turtle by experience. And even more, we will know that Achilles will catch the turtle when he has run a feet further than the turtle. Now the speed of Achilles is s feet per second, that of turtle is q times s feet per second for some q between 0 and 1. This means that in time t, Achilles will run s times t feet, and the turtle will run q times s times t feet. Hence Achilles will catch the turtle in time t, which satisfies s times t equals a plus q times s times t. This is easy to solve. We get that Achilles will catch the turtle in t equals a over s times 1 minus q seconds. We can do this computation because we assume that q is less than 1, hence 1 minus q is positive, and we can divide by it. So let us figure out where Achilles will catch the turtle. We have found out that Achilles will catch the turtle in t equals a over s times 1 minus q seconds. Since the speed of Achilles is s, we conclude that Achilles needs to run t times s, that is a divided by s times 1 minus q times s feet. Now s cancels out, and we conclude that Achilles must run a divided by 1 minus q feet to catch the turtle. Zeno's argument was that Achilles needs to run a plus a times q squared plus a times q cubed plus so on feet to catch the turtle. And Zeno argued that, well, this is an infinite sum. Achilles will never be able to run so far. But we have found out that Achilles will catch the turtle after Achilles has run a divided by 1 minus q feet. This means that this infinite sum, a plus a times q squared plus and so forth, really has a finite value, a divided by 1 minus q. This sum is also denoted mathematically by summation k from 0 to the infinity a times q to the power k. Hence we have derived a formula for the sum of a geometric series. This series, summation k from 0 to the infinity a times q to the power k, is called a geometric series. And a further argument will show that this formula is valid always when q is of absolute value less than 1, hence it is also valid for some negative values of q. Zeno's paradox is not really a paradox, but it is a way to find the summation formula for geometric series.